Okay, so year 11, last bit about waves. I hear you say, yay. However, today's sound, and sound is a little bit more interesting than light and water. So we're going to look at what are sound waves and how to investigate sound waves. So again, as usual, Caboodle textbook if you need it. Pages 142 to 143. There's some questions to test your knowledge, as well as some other different diagrams to support you. Quick quiz 1 to 7. Pause the slide now and let's see how we do. So question 1. Wave speed is meters per second. Wavelength is measured in meters and frequency is measured in hertz. What does the symbol lambda mean? It means wavelength. The equation for wave speed equals wavelength times frequency. And the equation for wavelength is wavelength equals wave speed divided by frequency. Remember to use your lovely equation triangle. And if we rearrange it again, flip that again, frequency equals wave speed divided by wavelength. What is the speed of the wave? So with a wavelength of 200 meters and a frequency of 0.05 hertz, it's 100 meters per second. Whereas with the wavelength of 2 meters and a frequency of 100 hertz, it's 200 meters per second. Awesome. Right, let's move on. So what is sound? Sound is a longitudinal wave, one of only the two examples you need to know, and it's made by vibrations in particles. So unlike electromagnetic waves that can travel through a vacuum, sound is required as a medium to travel through. So therefore, sound requires air particles to move or water particles. If there's no particles, it cannot travel. I'm sorry about the irritating noise. My rabbit has decided at this point to give an example of sound and how irritating it can be. Yeah. So here my sound vibrations move backwards and forwards. And as you can see, the vibration that moves from on the left-hand side of the screen hits the particles and they then collide and move, transferring the energy across. Now you may remember back in year 8 you did an experiment where you had a jar and we had a little alarm clock inside it and we sucked all the air out to show that sound requires those air particles to move. That is an experiment that we need you to remember and be able to explain if the need arises. So the speed of sound. So when two things collide together, it creates sound moving. And we can measure the speed of sound. Now, sound is very, very fast. However, sound is slower than light. You can measure the speed of sound just like you can measure the speed of anything. You need to know the distance and you need to know the time taken for it to travel. So, using the equation, speed equals distance divided by time, or we could put that into an equation triangle to calculate either the distance or the time. We know that 100 divided by 0.34 gives me 294 meters per second. And the speed of sound is about 300 meters per second in air. So, does that sound travel through all states of matter at the same speed? And what state does sound travel the fastest and why? So think about this. We've got our three states of matter here, solid, liquid, gas. And the particles in a solid are closer together than in a gas or a liquid. It means the vibrations are more easily passed from one particle to another. So sound travels faster through a solid. Visualizing sound waves. So sound waves are longitudinal and they look like this. Okay, they look like that compression wave that we saw with the slinky. But to visualize them, we need to convert them to waves that look like this, which is our trace on our oscilloscope that we talked about earlier. Now, if I match the oscilloscope to my acoustic wave, you can see it travels across, and you can see that wave moving across the screen, measuring peak to peak. Now, just like our ripple tank, this piece of equipment on the left-hand side of the screen is an oscilloscope. And our oscilloscope can tell us all sorts of things about sound waves. It can tell us how quiet or how loud a sound is. So the amplitude of our wave, this bit, the difference from here downwards, is our amplitude. Now, if we were describing the difference between a quiet and a loud sound, we would talk about that the loud sound has a greater amplitude. All right. So increasing the amplitude means that we increase the size of the height of the waves, therefore they look taller. When we're talking about pitch, this is a low pitch sound, so that's like a deep voice, and a high pitch sound, which would be a squeaky mouse-like noise. You can see that the amplitude is the same, however, the frequency of the waves is greater. So a high pitch has a higher frequency, so the waves look closer together. And these sounds are the same volume because the amplitude is the same. So when we think about the properties of sound can also be reflected off of surfaces. And this is very much what we would explain as an echo. You can use echoes to determine distance. You just have to double the distance, okay? And some animals use echo sounding location. And we also use echo sounding location in ships. And this transmits a high frequency sound that is reflected from the bottom of an ocean and is detected by the ship. And we use that to determine how deep or shallow the water is. Now, other animals, such as dolphins, use echolocation to communicate and work out where the rest of their pod are. Also, bats use echolocation to work out where objects are so that they don't collide into things. Don't always get it right, but they're pretty high degree of accuracy. So to calculate this distance, whether from a ship, dolphin or a bat, we need to know the time taken for the sound to be transmitted and received, the speed of the sound in the water or air, and you can use these to work out the depth of the water, which is half times T times V. Now we half T because we've looked at transmitting and receiving, so we only need one of those distances, okay? That works out a depth of water. The speed of sound in water is around 1500 meters per second. And we can see here that the pulse sent from the ship and the echo returned from the ship gives us speed. So the submarine sends out a sonar pulse and the traces the pulse of the echo shown. Each square on the oscilloscope represents 1 second. So we can see that between the pulse being sent and the pulse being received, we have 4 seconds. So 4 seconds equal 4 times 1 second equals 4 seconds. The depth of the water equals half times 4 times 1500, giving me 3000 meters. Exciting stuff, isn't it? So again, let's look at our pulse traces again. Each square on the oscilloscope now represents 0.5 seconds. And this is a different trace from the one we had before. So we count across 1, 2, 3, 4, 5, 6. 6 times 0.5. And we're still using the 1500 meters per second. We get 6 times 0.5 equals 3. Half T times V. Half times 3 times 1500. And I should say, and this goes without saying, but I appreciate it's a bit of a time since you did some real maths. So you should be using 0.5 if you're plugging this into a calculator. and that gives you 2,250 meters away, so the water has become shallower. So the same principle is for ultrasound imaging. That's if you're having a baby, okay? And when we're having an ultrasound, whether it's on your kidneys or a baby, or they even use these to do them on your heart as well. It has to be liquid, so it has to travel through liquid. So the ultrasound waves are partially reflective when they meet a boundary between two different materials. And as long as you know the speed of the sound of the material and the time taken for you to reflect, you can work out the depth. So here's my baby, not my personal baby, but here is the baby. And the ultrasound basically travels through the skin, through the blood, and when it hits the boundary, it is then reflected. It's reflected at different points. And that gives me my image. So this is a non-ionizing way of producing an image. Now, there is no radiation here that will cause any harm to the baby. It's totally non-invasive. So there's a real plus sign for using ultrasound for imaging, because it doesn't increase your chances of mutation, cellular mutation, as you would do with other types of imaging that are available. So, task 1. What I want you to do is pause the slide now, copy down the table using your equation, work out the blanks that are on the sheet. So just pause it now for me. And here are the answers. Awesome, as if by magic. Well done.